Hi everyone, welcome to the second of two videos going through some past exam questions on electrochemical cells and fuel cells. The first question we've got here talks about a fuel cell. So it says modern fuel cells are being developed as an alternative to the direct use of fossil fuels. Fuel can be hydrogen, but many other substances are being considered. In a methanol fuel cell, the overall reaction is combustion of methanol. As with all fuel cells, the fuel is supplied at one electrode and the oxygen is supplied at the other electrode. So oxygen reacts at the negative electrode like so. Write an equation for the complete combustion of methanol, okay, because it said that's the overall reaction. So methanol is going to be CH3OH. If it's combustion, it's reacting with oxygen, and if it's complete combustion, it's going to be carbon dioxide and water as the products. And then we just need to balance it, so it's only got one carbon. 4 hydrogens means I need to times that by 2, and we've got 4 oxygens in total here, and 1 oxygen there, so this needs to be 1.5 O2 to go there. It then says, deduce the half equation for the reaction that takes place at the positive electrode in a methanol fuel cell. So here what we want to do, we've seen this kind of question before if you've seen the other videos, is we want to do the overall equation, take away this half equation here. Okay. So if we write this out, this is the overall equation. And we're then going to subtract from that this half equation, which is going to go to 2H2O. So if we take this away, then we're going to end up with the methanol. Take away no methanol. We've got 1.5 O2, take away O2. So we've got plus half an O2. And then we've got minus 4H plus minus 4 electrons. And then on this side, we've got CO2 and the 2H2O take away the 2H2O, which is going to cancel out. So now what we need to do is just move this over to the other side. So we're going to end up with the methanol plus a half O2 goes to CO2 plus 4H plus 4 electrons. Okay, and that's going to be our other half equation. Finally, the last bit on this question then says, state 2 advantages of vehicles using fuel cells compared with the combustion of conventional fossil fuels. Okay, so here we want to be looking at things that make the fuel cells better. So the main thing I think from using a fuel cell is that there's less CO2 produced. Okay, that's the main problem with burning fossil fuels. Okay, and then the other problem is that the fuel cells are going to be much more efficient than burning the fossil fuels directly, right? That's why we use the fuel cells. So we could say fuel cells are more efficient. Okay, moving on. We then have a question here that says, this table shows 3 redox systems and their standard redox potentials. Draw a labeled diagram to show how the standard electrode potential of an SN4 plus SN2 plus redox system could be measured. Okay. Right, so then to measure this then we're going to have to set up a cell, and we're going to have the tin electrode as one of the electrodes, and then the other electrode is going to be the standard hydrogen electrode. Okay, that's how we're going to measure the standard cell potentials here. Okay, so we want our 2 beakers with our 2 electrodes. Okay. And on this side we're going to have our tin, so this is going to be a solution that contains SN4 plus, and it's going to contain SN2 plus. And if we look on this side, this is going to be a solution that is going to contain H plus ions. Okay. We're going to need to connect these up to a voltmeter so that we can measure the voltage. We're going to need to have a salt bridge in the middle. And then in both cases here, we're going to need to have a platinum electrode, because we've got 2 different ions of tin here, and here we can't have solid hydrogen as the electrode, but we're also going to have a container that is somehow over the top here. We're going to have a container which has got hydrogen gas in here. And then finally, because we're trying to measure the standard electrode potentials, we're going to have the concentrations of the solution being 1 mole per decimeter cubed. Okay, and that does matter. So we need 1 mole per decimeter cubed here, and with the tin 4 plus, and also with the tin 2 plus, that would have to be 1 mole per decimeter cubed as well. Okay, so quite a lot there to do to get 3 marks here. It then says, using the information in the table, write equations for the reactions that are feasible. Okay, suggest 2 reasons why these reactions may not actually take place. Okay, so again, we've got quite a bit to do here. We've got 5 marks, so at least they're giving us a decent chunk of marks for what's going on here. So if we're looking at what's going on here, then we've got 3 redox systems. So there's 3 possible reactions, right? If we call these A, B, and C, then we can look at the reaction between A and B. Okay, what's going to happen there is A is the more positive one out of the 2. So A is going to be reduced. Remember, that's the golden rule with all these electrode potentials. And B is going to be oxidized. So A is going to react from left to right. B is going to react from right to left. And if we're going to combine those 2 together to make one overall equation, we're going to have to make the electrons balance. So we're going to have to multiply this top one by 3. So it's going to be 3Cu plus the chromium, because it's going to react backwards. Do we need to write state symbols? No, it doesn't mention it, so I think we're okay here. That's going to make Cr3 plus and 3 coppers. Okay, and just check the charges balance, 3 plus and 3 plus. So that's that one. That's A and B. We do A and C. Then again, A is the more positive one, and we're going to have to multiply it by 2 this time to make the electrons balance out. So we're going to have 2Cu plus Sn2 plus. So again, because this is more positive, it's going from left to right. This one's more negative, so it's going from right to left. It's going to make Sn4 plus 2Cu. And again, we've got a 2 plus and 2 plus, so a 4 plus charge here and a 4 plus charge here. And then finally, if we combine B and C, then it's the tin that's the more positive one out of the 2. So that's going to be reduced, it's going to react from left to right. And this chromium one is going to go from right to left. And to make the electrons balance here, we're going to have to times this one by 2 and this one by 3. So we're going to have 3 Sn4 plus 2 chromiums is going to make 2 Cr3 plus 3 Sn2 plus. And again, 3 lots of 4 plus is a 12 plus charge, and we've got 6 plus and 6 plus there. Okay. So this was a 5-mark question. We've written 3 equations, that's presumably got us 3 marks. And so then it says suggest 2 reasons why these reactions may not take place. That's going to be our other 2 marks. Okay, so these reactions may not take place because well, all of this was based on the electrode potentials. Okay, and these were the standard electrode potentials. So if we're not doing it under standard conditions, then we're going to have different electrode potentials, and therefore a different reaction might happen. Okay, so the reactions may not take place under standard conditions. And then the other reason it always comes up with these is that, okay, even if you are doing it under standard conditions, maybe this reaction should happen in theory, but it might not actually happen because we also need to consider the rate of reaction. Okay, so we could say the rate of reaction may be very slow. And often we can go into a bit of detail of why, the main reason why the rate of reaction would be slow would be because the activation energy would be very high. Okay, and often you'd probably just get a mark for this. You might even be 2 points to say reaction is very slow because the activation energy is very high. But I just want to write the best answer that I can, because the activation energy may be very high. Okay. Right, moving on. We've got a question here where, again, they've given us a pile of electropotentials to have a look at. I'm not going to worry about reading this. What does it say? Standard electropotential of redox system 1 can be measured by constructing electrochemical cell. Draw a diagram to show how the standard electropotential could be measured. Okay, so this is almost exactly the same question as we just saw. Okay, we need to draw a cell, and it's going to be whatever's going on in redox system 1 and the standard hydrogen half cell is going to be the other one. You know, if we're trying to measure the electropotentials, then we need to be using the standard hydrogen half cell. Okay, so we're going to do a similar thing here. Where we want our 2 beakers. I'm actually going to draw this over the top here, because this is going to be our container that needs to have the hydrogen gas in it. And we've got our 2 electrodes and a solution. And my pen's running out. Okay, and so this is going to have to be a 1 mole per decimeter cubed solution of H+ ions. And this is going to have to be a platinum electrode. These are going to have to be connected up with a voltmeter so that we can measure the voltage. We're going to have some kind of salt bridge here. You can see that the quality of the diagram doesn't really matter, thankfully, because, I mean, this is a mess. But as long as you've labelled everything up, so you're showing that you understand what it should be, they're not going to mark you for how good your drawing skills are, thankfully. So that's our standard hydrogen electrode, and then this needs to be redox system 1, which is this iron. It's Fe2+, and Fe is a solid. So therefore, this is going to be a solid iron electrode. And then this is going to be a solution of 1 mole per decimeter cubed, Fe2+. Okay. And then it says, state the conditions needed to measure this standard electropotential. So it needs to be at the standard temperature of 298 Kelvin. It needs to be at a standard of 1 atmospheric pressure. Or you can do this in degrees C, you can do this in kilopascals. It doesn't matter. And the solutions need to be 1 mole per decimeter cubed, which we've kind of already put on our diagram, so I'm not sure we need to say that again, but it won't do any harm, just to make sure we've made that really clear. Okay, this next question is quite a nice one. I want to show you this question because we need to be really careful here, because there's some key information in the question that we need to make sure we've looked at. Okay. So the key thing here is where it says here, when an alkaline hydrogen-oxygen fuel cell, this pen's running out as well, an alkaline hydrogen-oxygen fuel cell is being used, write half equations for what's going on at each electrode. That matters. Okay, if we go up and look at this, you'll see why, because basically all of these electropotentials, apart from the top one, have got oxygen, hydrogen, water that are all kind of the same thing. So how do we know what's going on here? It's got to be the alkaline ones. Okay, so what's the alkaline oxygen one? So we're looking for something with oxygen and an alkali in it. So we're looking for oxygen gas here and an alkali OH-. So it's this one, redox system 4. And the alkaline hydrogen electrode, again, is one that wants to be hydrogen gas and alkali. So it's going to be this one here, number 2. Okay, it's not going to be 3 because that would be under acid conditions, and similarly 5 would be under acid conditions. Okay, so it's 2 and 4. But then the question said, write half equations for the changes that take place, right? They're not just going to want you to write the equilibrium out because you've just copied it. Which way is this actually going to be? If we look at 2 and 4, 4 is the positive one out of the 2. Okay, so this oxygen electrode is going to go from left to right. So I can copy this out just with an arrow instead of the equilibrium symbol. Okay, so it's going to be O2 plus 2H2O plus 4 electrons goes to 4OH minus. And then the hydrogen electrode, I'm going to copy this equation but backwards because it's the negative one out of the 2. So it's going to be oxidized. So it'll be H2 plus 2OH minus produces 2H2O and 2 electrons. Okay. And then it wants us to write the overall equation for the cell reaction. So this would be combining these two together. So to make that work, we'd have to multiply this equation by 2 to get the electrons to balance out. And then we'd add them together. Okay, so we'd get H2 plus 4OH minus. But that 4OH minus would then cancel with this. Yeah, I've multiplied this by 2, haven't I? To make this 4OH minus. So that would cancel out. So we don't need to worry about that. And then we'd have our O2. We'd have 2H2O here, but we would then have, because I've multiplied this one by 2, I'd have 4H2O on the other side. So actually this wouldn't be here either. So, I've multiplied this equation by 2 as well, haven't I? So I should have 2H2. And then here I'd get the 4OH minuses would cancel out. The electrons would obviously cancel out. And I'd end up with 4H2O on this side, but I'd have 2H2O on that side, so I'd have a net 2H2O here. Okay, and you should find that's a balanced equation. Okay. So this question carries on. It then says, what is the standard cell potential of this fuel cell? So the cell potential we need to work out from looking at the electrode potentials from here. So it was 2 and 4, wasn't it? So it's minus 0.83 and plus 0.4. So remember the cell potential is the difference between the two. So what we want to do is plus 0.4 minus 0.83. So it should be 1.23 volts. Okay. State one important difference between a fuel cell and a conventional storage cell. So this is basically, again, if you've seen the other video, I think this is word for word the same question. It's really asking you what's the definition of a fuel cell. Okay. So in a fuel cell, a fuel reacts with oxygen to generate a voltage. People often assume that hydrogen-oxygen fuel cells are a source of energy that's carbon neutral, i.e. there's no net increase in carbon dioxide. Suggests one reason why this assumption may not be correct. So the main reason for this then is, where do we get the hydrogen from in the first place? Okay. The good thing is that these fuel cells don't produce a lot of carbon dioxide, but there may be carbon dioxide produced in making the hydrogen fuel in the first place. Okay. So fossil fuels may be used, and carbon dioxide may be produced to make the hydrogen fuel. It's only one mark question, so that's as much detail as we need. Okay, finally the last question we're going to look at here says, student constructs a cell. A half cell is made from a strip of chromium metal and a solution of aqueous chromium 3 sulfate. Second half cell is made from a strip of metal X and a solution of X SO4. The two half cells are connected together and a current is allowed to pass. The chromium electrode gains 1.456 grams in mass. The electrode made of metal X loses 1.021 grams. Determine the identity of metal X. Okay, so the first thing we can do here is, looking at metal X, we know it's made a solution of X SO4. So if that's the case, well, I know that a sulfate ion is SO4 2-, right? So metal X must be X2 plus. So it must be some kind of group 2 metal. Well, it could be a transition metal, I suppose. So actually, let's put that in brackets. It's likely to be a group 2 metal, but it could be a transition metal, couldn't it? There's a 2 plus ion. So we don't want to be too confident about that. But it's definitely a 2 plus ion. What we can do is we can use this mass, can't we? Because we know the chromium electrode is just made from solid chromium metal. So we can calculate the number of moles. It's always a good place to start, is calculate the number of moles of something. So if we divide that by the relative atomic mass of chromium, which is 52, that will give us the moles of chromium. So we get 0.028 moles of chromium produced. So that's how much this electrode increases in mass. And then we know that what must be happening is the chromium 3 sulfate. So if this is increasing in mass, this must be going from chromium 3 to ordinary chromium. And so therefore, what must be happening is metal X must be doing the opposite. Metal X must be doing X goes to X2 plus 2 electrons. So therefore, these are our two half equations. If we combine those together, the overall equation must be 2Cr3 plus, because we're going to have to times this by 2 and multiply that by 3. Yeah. So it must be 2Cr3 plus 3x goes to 3x2 plus 2Cr. So therefore, it's a 2 to 3 ratio. So the moles of X that react is going to be 0.028 divided by 2 times by 3. Okay. So it's 0.042 moles. And then we can work this out because we know the mass. So we can do that divided by that. And that will give us the atomic mass, which will allow us to identify what the metal is. So if we do 1.021 divided by 0.042, 24.3. So we're looking for something with a mass of 24.3, and it's probably from group 2, so that matches up nicely with magnesium. Okay, it's 24.3. and it's group 2. So X must be magnesium.